Aerospace Engineering: The Basics of Aerodynamics, Unmanned Aerial Vehicles. Written by Phil Gilbert. Narrated by Kevin Brooker. 1. Introduction to Aerospace Engineering. Aerospace engineering encompasses a broad range of disciplines, including aerodynamics, which studies how air flows around objects like aircraft wings, propulsion systems, which power vehicles through the atmosphere or space, materials science, which focuses on developing lightweight yet durable materials for airspace applications, and avionics, which involves designing and implementing electronic systems for navigation, communication, and control. Additionally, aerospace engineers work on structural design to ensure that vehicles can withstand the stresses of flight and space travel, as well as thermal management to regulate temperatures in extreme environments. They also contribute to the development of guidance and control systems to maintain stability and control during flight. Moreover, aerospace engineering extends beyond Earth's atmosphere, with space exploration being a significant area of focus. This includes designing spacecraft for missions to satellites, communication and observation, etc. Overall, aerospace engineering plays a crucial role in advancing our understanding of the universe and expanding our capabilities beyond the confines of our planet. 2. Fundamentals of aerodynamics. Let's delve deeper into some of the key concepts with the fundamentals of aerodynamics. 1. Fluid dynamics. Aerodynamics is a branch of fluid dynamics, which studies the behavior of fluids, or liquids and gases, in motion. Engineers analyze how air flows around objects like aircraft wings or rocket bodies. This analysis involves understanding complex phenomena such as laminar and turbulent flow, boundary layers, and vortices. 2. Lift and drag. Lift is the force that enables an aircraft to rise into the air, counteracting the force of gravity. Drag, on the other hand, is the resistance experienced by an aircraft as it moves through the air. Aerodynamic engineers study the factors affecting lift and drag, including wing shape, angle of attack, and airfoil design, to optimize aircraft performance. 3. Aerodynamic forces. In addition to lift and drag, other aerodynamic forces influence an aircraft's motion. These include thrust, which propels the aircraft forward, and weight, which opposes lift. Engineers must carefully balance these forces to achieve stable flight. 4. Stability and control. Aerodynamics also play a crucial role in an aircraft's stability and controllability. Engineers design aircraft with features like horizontal and vertical stabilizers, control surfaces such as ailerons, elevators, and rudders, and fly-by-wire systems to ensure safe and precise maneuverability. 5. Transonic and supersonic flow. As aircraft approach the speed of sound, transonic, and exceed it, supersonic, aerodynamic behavior changes significantly. Engineers must account for phenomena like shock waves, compression effects, and drag divergence to design aircraft capable of high-speed flight. 6. Computational aerodynamics. With advancements in computational fluid dynamics, or CFD, engineers can simulate and analyze airflow around complex geometries digitally. This enables them to refine designs, optimize performance, and troubleshoot aerodynamic issues before physical testing. 7. Applications beyond aviation. While aerodynamics is foundational to aviation, its principles also apply to other fields, such as automotive design for cars and racing vehicles, wind turbine technology, and even sports equipment like cycling helmets and golf balls. Understanding these fundamental concepts is essential for aerospace engineers to design aircraft, spacecraft, and other aerodynamic systems that meet performance, efficiency, and safety requirements. 3. Principles of flight. The principles of flight are the fundamental concepts that explain how aircraft and other flying objects achieve lift, propulsion, stability, and control. These principles are crucial for understanding the mechanics of flight and designing aircraft capable of safe and efficient operation. Here are the key principles. 1. Lift. Lift is the force that enables an aircraft to overcome gravity and stay airborne. It is generated primarily by the wings through the Bernoulli's principle and Newton's third law of motion. The shape of the wing or airfoil, angle of attack, and airspeed influence lift generation. 2. Thrust. Thrust is the force that propels an aircraft forward. It is typically generated by engines, propellers, or jet turbines. Thrust must exceed drag to accelerate the aircraft and maintain forward motion. 3. Drag. Drag is the aerodynamic resistance encountered by an aircraft as it moves through the air. It opposes thrust and includes various forms such as parasitic drag, caused by the aircraft's shape, induced drag, or caused by lift production, and wave drag, caused by supersonic flight. 4. Weight. Weight is the force exerted by gravity on an aircraft. It acts downward through the aircraft's center of gravity and must be balanced by lift to maintain level flight. Proper weight distribution is essential for stability and control. 5. Stability. Stability refers to an aircraft's tendency to return to its original state after being disturbed. Longitudinal stability involves maintaining a consistent pitch attitude, while lateral stability involves maintaining a consistent roll attitude. Engineers design aircraft with stability augmentation systems to ensure safe and predictable flight characteristics. 6. Control. Control refers to the ability to maneuver an aircraft in 3 dimensions: pitch, roll, and yaw. Aircraft control surfaces, such as ailerons, elevators, and rudders, are used to change the aircraft's orientation and direction of motion. Pilots manipulate these controls to perform maneuvers and maintain stability. 7. Center of gravity. The center of gravity is the point where the aircraft's weight is concentrated. It plays a crucial role in determining the aircraft's stability and maneuverability. Engineers carefully calculate and control the center of gravity to ensure safe flight characteristics. Understanding these principles allows aerospace engineers to design aircraft that can effectively overcome gravity, maintain stable flight, and respond to pilot inputs. Moreover, pilots rely on these principles to operate aircraft safely and efficiently in various flight conditions. 4. Aircraft performance. Aircraft performance encompasses a range of factors that determine how an aircraft behaves in flight, including its speed, range, payload capacity, fuel efficiency, climb rate, and maneuverability. Understanding and optimizing aircraft performance is crucial for designing aircraft that meet operational requirements and regulatory standards. Here are some key aspects of aircraft performance. Speed. Aircraft speed can vary widely depending on the type of aircraft and its intended mission. Performance parameters related to speed include maximum speed, often measured in Mach number for high-speed aircraft, cruising speed, and stall speed, the minimum speed required to maintain level flight. Range. Range refers to the distance an aircraft can travel on a single tank of fuel. Factors influencing range include fuel efficiency, aerodynamic efficiency, and payload weight. Engineers optimize aircraft design to maximize range while meeting other performance criteria. Payload capacity. Payload capacity is the maximum weight of passengers, cargo, and fuel that an aircraft can carry while still meeting performance requirements. Aircraft with higher payload capacities are capable of carrying more passengers or cargo over longer distances. Fuel efficiency. Fuel efficiency is a critical aspect of aircraft performance, as fuel consumption directly impacts operating costs and environmental impact. Engineers use aerodynamic design, lightweight materials, and efficient propulsion systems to maximize fuel efficiency. Climb rate. Climb rate refers to the rate at which an aircraft can ascend vertically. A higher climb rate allows an aircraft to reach cruising altitude more quickly, reducing fuel consumption and flight time. Maneuverability. Maneuverability refers to an aircraft's ability to change direction and attitude in flight. Factors influencing maneuverability include wing design, control surface effectiveness, and engine thrust-to-weight ratio. High maneuverability is essential for military aircraft and aerobatic performers. Takeoff and landing performance. Takeoff and landing performance depends on factors such as runway length, aircraft weight, and environmental conditions. Engineers design aircraft with appropriate takeoff and landing speeds, runway requirements, and braking systems to ensure safe and efficient operations. Optimizing aircraft performance involves trade-offs between various factors, such as speed versus fuel efficiency or payload capacity versus range. Engineers use computational modeling, wind tunnel testing, and flight testing to evaluate different design configurations and select the optimal balance of performance characteristics for each aircraft. Additionally, ongoing advancements in materials, propulsion systems, and aerodynamics continue to push the boundaries of aircraft performance, enabling faster, more efficient, and more capable aircraft designs. 5. Design considerations for unmanned aerial vehicles or UAVs. Designing unmanned aerial vehicles or UAVs, also known as drones, involves several unique considerations compared to manned aircraft. Here are some key design considerations for UAVs. Mission requirements. UAV design begins with a clear understanding of the mission requirements, such as surveillance, reconnaissance, cargo delivery, or scientific research. The design must align with the UAV's intended tasks and operational environment. Size and weight. UAVs come in a variety of sizes, from small quadcopters to large, fixed-wing aircraft. The size and weight of the UAV impact factors such as payload capacity, flight time, and maneuverability. Designers must balance size and weight constraints with mission requirements. Flight time and range. Maximizing flight time and range is crucial for many UAV missions, particularly those requiring long-endurance surveillance or long-distance transport. Design considerations include aerodynamic efficiency, propulsion system efficiency, and fuel or battery capacity. Payload capacity. UAVs often carry payloads such as cameras, sensors, communication equipment, or cargo. Designers must ensure that the UAV has sufficient payload capacity to carry the necessary equipment while maintaining stability and performance. Flight control systems. Unlike manned aircraft, UAVs are typically controlled remotely or autonomously. Designers must incorporate robust flight control systems that enable precise control and navigation, as well as redundancy to ensure safe operation in case of system failures. Communication systems. UAVs rely on communication systems to receive commands from operators and to transmit data back to the ground stations. Design considerations include communication range, bandwidth, reliability, and security. Durability and reliability. UAVs may operate in challenging environments, including extreme temperatures, high altitudes, or adverse weather conditions. Designers must ensure that the UAV is durable and reliable enough to withstand these conditions and operate effectively for extended periods. Stealth and low observability. Some UAV missions require stealth or low observability to avoid detection by adversaries or minimize disruption to the environment. Design considerations include reducing radar cross-section, minimizing acoustic signatures, and employing camouflage or countermeasures. Autonomy and artificial intelligence. Advances in autonomy and artificial intelligence enable UAVs to perform increasingly complex tasks with minimal human intervention. Designers must incorporate sensors, algorithms, and decision-making capabilities to enable autonomous operation while ensuring safety and compliance with regulations. Regulatory compliance. UAV design must comply with relevant regulations and standards governing airspace access, safety, privacy, and environmental impact. Designers must consider regulatory requirements from the initial concept phase through the certification and operation. By carefully addressing these design considerations, engineers can develop UAVs that effectively meet mission requirements, operate reliably and safely, and contribute to a wide range of civilian and military applications. Six, aerodynamic characteristics of UAVs. The aerodynamic characteristics of UAVs are crucial for their performance, stability, and efficiency. Unlike manned aircraft, UAVs come in various shapes and configurations, each with unique aerodynamic properties. These properties affect how the UAV moves through the air, its maneuverability, and its ability to carry out its intended mission. UAVs can be broadly categorized into fixed-wing and rotary-wing, such as quadcopters, configurations, each with distinct aerodynamic characteristics. Fixed-wing UAVs rely on lift generated by their wings to maintain flight, while rotary-wing UAVs generate lift through rotating blades. For fixed-wing UAVs, aerodynamic considerations include wing design, airfoil selection, and wing loading. Engineers optimize wing shape and aspect ratio to achieve desired lift-to-drag ratios and stall characteristics. Control surfaces such as ailerons, elevators, and rudders are used to control roll, pitch, and yaw. Rotary wing UAVs, on the other hand, rely on rotor blades to generate lift and thrust. Aerodynamic considerations for rotary wing UAVs include rotor design, blade pitch, and rotor disc loading. Control of rotary wing UAVs is achieved through varying rotor blade pitch, rotor speed, and rotor orientation. Additionally, UAV designers must consider aerodynamic stability and control. Longitudinal stability, lateral stability, and directional stability are essential for maintaining straight and level flight and for maneuvering the UAV as needed. Control surfaces, stability augmentation systems, and flight control algorithms are used to achieve desired stability and control characteristics. Furthermore, Aerodynamic characteristics influence other aspects of UAV design, such as payload capacity, endurance, and mission versatility. Optimizing aerodynamic performance allows UAVs to operate more efficiently, fly longer distances, and carry heavier payloads while maintaining stability and maneuverability. Overall, understanding and optimizing the aerodynamic characteristics of UAVs is essential for designing UAVs that meet mission requirements, operate reliably and efficiently, and perform effectively in a variety of environments and conditions. 7. Propulsion systems for UAVs. Propulsion systems for UAVs play a critical role in determining their performance, endurance, and mission capabilities. There are several types of propulsion systems commonly used in UAVs, each with its own advantages and considerations. Electric motors. Electric propulsion systems are popular for small to medium-sized UAVs, particularly quadcopters and multirotors. They are lightweight, efficient, and relatively quiet. Electric motors are powered by batteries, providing clean and renewable energy sources. However, limited battery capacity can restrict flight endurance, and recharging or replacing batteries is necessary for extended missions. Internal combustion engines. Internal combustion engines, such as gasoline or diesel engines, are used in larger fixed-wing UAVs and some rotary-wing UAVs. They offer higher power-to-weight ratios and longer flight endurance compared to electric motors. However, they require fuel, produce emissions, and require more maintenance. Turbine engines. Turbine engines, including turbojets, turbofans, and turboprops, are used in larger and higher performance UAVs, including military drones and commercial UAVs. Turbine engines provide high thrust-to-weight ratios, allowing for high speeds and heavy payloads. However, they are complex, expensive, and require specialized maintenance. Hybrid systems. Hybrid propulsion systems combine multiple power sources, such as electric motors and internal combustion engines, to leverage the advantages of each. For example, a hybrid UAV may use an electric motor for low speed, long-endurance flight, and switch to an internal combustion engine for high-speed or heavy lift operations. Hybrid systems offer flexibility and efficiency, but may be more complex and costly to develop and maintain. Solar power. Solar-powered UAVs harness energy from sunlight using photovoltaic cells to power electric motors or charge onboard batteries. They offer extended endurance and are ideal for long-duration missions, such as environmental monitoring or telecommunications relay. However, solar-powered UAVs are limited by available sunlight and may require large wing areas for sufficient solar panel coverage. Fuel cells. Hydrogen fuel cells convert hydrogen gas and oxygen into electricity, with water vapor as the only byproduct. Fuel cell-powered UAVs offer high energy density and long endurance, making them suitable for extended missions. However, Hydrogen storage and refueling infrastructure can be challenging, and fuel cells require careful handling and maintenance. Each propulsion system has its own trade-offs in terms of performance, efficiency, reliability, and operating costs. UAV designers must carefully select the propulsion system that best suits the mission requirements, considering factors such as flight endurance, payload capacity, operating environment, and regulatory constraints. Additionally, advancements in propulsion technology, such as electric propulsion efficiency and energy storage capabilities, continue to drive innovation in UAV design and performance. 8. Control systems and flight dynamics. Control systems and flight dynamics are essential components of unmanned aerial vehicles, or UAVs, that govern their stability, maneuverability, and overall performance. Here's an overview of each. Control systems. UAVs rely on sophisticated control systems to maintain stability, adjust flight parameters, and execute maneuvers. These control systems can be categorized into two main types. Manual control. In manual control systems, human operators, often called pilots or operators, directly manipulate control inputs to guide the UAV. These inputs can include commands for pitch, roll, yaw, and throttle. Manual control is common in smaller UAVs and is typically employed for tasks requiring real-time decision-making or precise maneuvering. Autonomous control. Autonomous control systems enable UAVs to operate with varying degrees of autonomy, ranging from semi-autonomous to fully autonomous operation. These systems rely on sensors, onboard computers, and algorithms to interpret environmental data, make decisions, and adjust flight parameters accordingly. Autonomous UAVs can perform tasks such as waypoint navigation, obstacle avoidance, and mission planning without direct human intervention. Flight dynamics. Flight dynamics describe the behavior of an aircraft in response to external forces and control inputs. Key concepts within flight dynamics include stability. Aircraft stability refers to its tendency to return to a steady state following disturbances. Longitudinal stability involves stability in pitch, or nose-up or nose-down motion. Lateral stability involves stability in roll, or side-to-side motion. And directional stability involves stability in yaw, or turning motion. Stability is essential for safe and predictable flight. Maneuverability. Maneuverability describes an aircraft's ability to change its flight path or attitude in response to control inputs. It is influenced by factors such as wing design, control surface effectiveness, and thrust-to-weight ratio. High maneuverability enables UAVs to perform agile maneuvers and adapt to changing mission requirements. Aerodynamics. Aerodynamics plays a crucial role in flight dynamics as it governs the generation of lift, drag, and other aerodynamic forces. Understanding aerodynamic principles such as airfoil design, airflow patterns, and stall characteristics is essential for optimizing UAV performance and stability. Control response. Control response refers to the aircraft's reaction to control inputs, such as how quickly it responds and how smoothly it transitions between maneuvers. Control response is influenced by factors such as control surface effectiveness, aircraft inertia, and stability augmentation systems. Overall, control systems and flight dynamics are interconnected aspects of UAV design that work together to ensure safe, stable, and efficient flight operations. Engineers must carefully design and integrate control systems that effectively manage flight dynamics while meeting mission requirements and operational constraints. Advances in control system technology, flight dynamics modeling, and autonomy continue to drive innovation in UAV design and performance capabilities. 9. Navigation and guidance systems. Navigation and guidance systems are crucial components of unmanned aerial vehicles, or UAVs, that enable them to navigate autonomously, follow predefined routes, and to execute mission objectives. These systems rely on a combination of sensors, algorithms, and communication technologies to determine the UAV's position, orientation, and velocity, and provide accurate guidance commands. Here's an overview of navigation and guidance systems for UAVs. Navigation systems. UAV navigation systems determine the vehicle's position and orientation relative to its surroundings. Common navigation sensors include GPS, or Global Positioning System, which provides accurate position information based on satellite signals, and Inertial Measurement Units, or IMUs, which measure the UAV's acceleration and rotation rates. Additionally, UAVs may use other sensors such as magnetometers, altimeters, and cameras for additional navigation information, particularly in environments where GPS signals are unavailable or unreliable. Guidance systems. UAV guidance systems determine the optimal flight path and provide commands to control the vehicle's trajectory. These systems rely on algorithms that process navigation data and generate guidance commands to steer the UAV toward its destination while avoiding obstacles and adhering to mission constraints. Guidance algorithms may incorporate waypoint navigation, path planning, obstacle detection and avoidance, and dynamic rerouting to adapt to changing environmental conditions or mission objectives. Autonomous operation. Many UAVs operate autonomously, meaning they can navigate and execute missions without direct human intervention. Autonomous operation requires sophisticated navigation and guidance systems capable of interpreting sensor data, making decisions, and executing commands in real time. These systems enable UAVs to perform tasks such as surveillance, mapping, inspection, and delivery with minimal human oversight, increasing efficiency and reducing the need for continuous human control. Communication systems. Communication systems play a crucial role in UAV navigation and guidance, enabling data exchange between the UAV and ground-based control stations or other aircraft. Communication links transmit navigation data, command inputs, and telemetry information, allowing operators to monitor the UAV's status and issue commands remotely. Reliable communication is essential for maintaining situational awareness, coordinating multiple UAVs, and ensuring safe and effective mission execution. Integration and redundancy. UAV navigation and guidance systems are often integrated with other onboard systems, such as flight control systems, sensors, and payloads, to enable seamless operation and mission coordination. Redundancy measures such as backup sensors, redundant communication links, and fail-safe mechanisms are implemented to enhance system reliability and mitigate the risk of system failures or malfunctions. Overall, navigation and guidance systems are critical enablers of UAV autonomy and mission effectiveness. Advances in sensor technology, algorithm development, and communication protocols continue to improve the capabilities and reliability of UAV navigation and guidance systems, expanding the range of applications and opportunities for unmanned aerial vehicles. 10. Sensors and payloads for UAVs. Sensors and payloads are essential components of unmanned aerial vehicles, or UAVs, that enable them to gather data, perform tasks, and fulfill mission objectives. These systems encompass a wide range of technologies tailored to specific applications and operational requirements. Here's an overview of sensors and payloads commonly used in UAVs. Imaging sensors. Imaging sensors capture visual data, including still images and video footage, for applications such as surveillance, reconnaissance, mapping, and inspection. Common imaging sensors include visible light cameras, infrared cameras or thermal imaging, multispectral cameras for vegetation analysis, and hyperspectral cameras for detailed spectral analysis. LiDAR or LiDAR, light detection and ranging. LiDAR sensors use laser pulses to measure distances and generate high-resolution 3D maps of terrain, structures, and objects. LiDAR is used for topographic mapping, terrain modeling, infrastructure inspection, and obstacle detection in UAV applications. Radar or radio detection and ranging. Radar sensors emit radio waves to detect and track objects, measure their distance and velocity, and penetrate obstacles such as foliage or buildings. UAV-mounted radar systems are used for ground surveillance, target detection, collision avoidance, and weather monitoring. Global Navigation Satellite Systems, or GNSS. GNSS receivers, such as GPS or Global Positioning System, GLONASS, or GLONASS, and Galileo, provide accurate positioning and timing data to determine the UAV's location and navigate along predefined flight paths. GNSS is essential for autonomous navigation, waypoint navigation, and geotagging of sensor data. Inertial Measurement Units, or IMUs. IMUs consist of accelerometers and gyroscopes that measure the UAV's acceleration and rotation rates, respectively. IMUs provide information about the UAV's attitude or orientation and motion dynamics, aiding in stabilization, navigation, and control. Environmental sensors. Environmental sensors measure various parameters, such as temperature, humidity, pressure, air quality, and radiation levels. These sensors are used for environmental monitoring, pollution detection, weather forecasting, and scientific research. Communication systems. Communication payloads enable data transmission between the UAV and ground-based control stations, other aircraft, or remote users. Communication systems include radio links, satellite links, cellular networks, and Wi-Fi connections, facilitating command and control, telemetry, video streaming, and data sharing. Payload delivery systems. Payload delivery systems enable UAVs to transport and deploy payloads such as supplies, sensors, or equipment. Payload delivery mechanisms include drop systems, release mechanisms, and landing platforms, allowing UAVs to perform tasks such as cargo delivery, medical supply transport, or search and rescue operations. Custom payloads. UAVs can be equipped with custom payloads tailored to specific applications or research objectives. Examples include gas sensors for detecting chemical leaks, radiation detectors for nuclear monitoring, magnetometers for mineral exploration, and sonar systems for underwater mapping. By selecting and integrating appropriate sensors and payloads, UAV operators can customize their systems to meet diverse mission requirements ranging from aerial photography and surveillance to environmental monitoring and disaster response. Advances in sensor technology, miniaturization, and payload integration continue to expand the capabilities and versatility of UAVs for civilian, commercial, and military applications. 11. Integration and testing of UAVs. Integration and testing of UAVs are critical phases in the development cycle that ensures the system operates safely, reliably, and effectively. These processes involve assembling the UAV components, verifying their functionality, and validating the system's performance under various conditions. Here's an overview of integration and testing activities for UAVs. Component integration. UAV integration begins with assembling the individual components, including airframe, propulsion system, avionics, sensors, communication systems, and payloads. Each component is installed, connected, and configured according to the UAV's design specifications. System integration. Once the individual components are assembled, they are integrated into the complete UAV system. This involves connecting subsystems, wiring electrical connections, mounting sensors and payloads, and ensuring compatibility and interoperability between components. Functional testing. Functional testing verifies that each component and subsystem operates correctly and meets performance requirements. This includes testing propulsion system startup and shutdown, sensor calibration, communication link establishment, flight control system functionality, and payload operation. System verification. System verification testing assesses the overall functionality and performance of the integrated UAV system. This involves conducting ground tests and simulating flight tests to verify system behavior, identify potential issues, and validate system-level requirements. Flight testing. Flight testing is conducted to evaluate the UAV's performance in real-world operating conditions. Flight tests assess flight dynamics, stability, maneuverability, navigation accuracy, payload performance, and overall system reliability. Flight tests may include takeoff and landing tests, hover tests, waypoint navigation tests, and mission simulation tests. Environmental testing. Environmental testing evaluates the UAV's performance in various environmental conditions, such as temperature extremes, humidity, wind, rain, and altitude. Environmental tests assess the UAV's resilience to environmental factors and ensure that it can operate safely and reliably under different scenarios. Safety testing. Safety testing evaluates the UAV's compliance with safety regulations and standards, including airworthiness requirements, collision avoidance capabilities, emergency procedures, and fail-safe mechanisms. Safety tests identify potential hazards and assess risk mitigation measures to ensure safe operation. Regulatory compliance. Regulatory compliance testing ensures that the UAV meets legal and regulatory requirements for airspace access, operational limitations, communication protocols, and data privacy. Compliance testing may involve obtaining certifications, permits, or approvals from aviation authorities or regulatory agencies. Performance optimization. Throughout the integration and testing process, engineers identify opportunities to optimize the UAV's performance, efficiency, and reliability. This may involve refining control algorithms, adjusting sensor configurations, optimizing payload placement, or upgrading components to enhance system capabilities. By rigorously conducting integration and testing activities, UAV developers can ensure that their systems meet quality standards, perform as intended, and comply with regulatory requirements. Integration and testing play a crucial role in minimizing risks, validating design decisions, and delivering UAVs that meet customer expectations and mission objectives. 12. Applications of UAVs in aerospace engineering. Unmanned aerial vehicles, or UAVs, have revolutionized aerospace engineering by expanding the scope of applications and capabilities within the field. Here are some key applications of UAVs in aerospace engineering. Surveillance and reconnaissance. UAVs are extensively used for surveillance and reconnaissance missions, providing real-time imagery, video footage, and intelligence data for military, law enforcement, and security operations. They offer persistent aerial surveillance capabilities without risking human lives and can access remote or hazardous areas with ease. Mapping and geospatial analysis. UAVs equipped with imaging sensors, LiDAR systems, and GPS technology are utilized for mapping, surveying, and geospatial analysis. They generate high-resolution 3D maps, terrain models, and orthomosaic images for urban planning, land surveying, environmental monitoring, and disaster response applications. Agriculture and crop monitoring. UAVs are employed in agriculture for crop monitoring, pest detection, irrigation management, and yield estimation. Multispectral and thermal imaging sensors mounted on UAVs provide valuable insights into crop health, soil moisture levels, and vegetation indices, enabling farmers to optimize crop production and resource utilization. Infrastructure inspection and maintenance. UAVs are used for inspecting critical infrastructure such as bridges, dams, pipelines, power lines, and buildings. They can access hard-to-reach or hazardous structures, capture high-resolution imagery, and detect structural defects, corrosion, or damage, facilitating proactive maintenance and safety assessments. Search and rescue operations. UAVs play a vital role in search and rescue missions, particularly in disaster response scenarios. Equipped with thermal imaging cameras, UAVs can detect heat signatures from survivors, map disaster-affected areas, and deliver supplies or communication equipment to remote locations, expediting search and rescue efforts and saving lives. Environmental monitoring and conservation. UAVs support environmental monitoring and conservation efforts by conducting aerial surveys, wildlife tracking, habitat mapping, and pollution monitoring. They provide valuable data for studying ecosystems, monitoring biodiversity, detecting illegal activities such as poaching or deforestation, and assessing the impact of climate change on natural resources. Meteorological research and atmospheric science. UAVs are utilized in meteorological research and atmospheric science to collect atmospheric data, study weather patterns, and monitor environmental conditions. They can deploy sensors, sondes, and instruments to measure temperature, humidity, pressure, wind speed, and atmospheric composition, contributing to weather forecasting, climate modeling, and scientific research. Space exploration and planetary science. UAVs are employed in space exploration missions to explore planetary surfaces, conduct aerial surveys, and collect scientific data in extraterrestrial environments. Mars rovers, lunar landers, and unmanned aerial vehicles such as drones, are used to study planetary geology, search for signs of life, and prepare for perhaps possible future human exploration missions. These applications demonstrate their versatility, efficiency, and transformative impact of UAVs in aerospace engineering, advancing scientific research, enhancing operational capabilities, and addressing societal challenges across various domains. As UAV technology continues to evolve, the potential for innovation and discovery within aerospace engineering continues to expand, opening new frontiers in exploration, observation, and discovery. 13. Future trends and challenges in UAV technology. Future trends and challenges in UAV technology are influenced by ongoing advancements in hardware, software, regulations, and applications. One significant trend is the increasing autonomy and integration of artificial intelligence, or AI, in UAVs, enabling them to perform complex tasks with minimal human intervention. Challenges in this area include developing robust algorithms for real-time decision-making, ensuring safety and reliability in dynamic environments, and addressing ethical and legal implications. Another trend is the emergence of UAV swarms, consisting of multiple coordinated drones for various applications such as surveillance and search and rescue. Future developments include refining algorithms for swarm coordination, communication, and task allocation, as well as addressing scalability and robustness challenges. Beyond visual line of sight, or BVLOS, operations represent another area of interest, enabling UAVs to fly beyond the operator's line of sight. This unlocks new opportunities for aerial inspections, delivery services, and long-range missions. Challenges include developing reliable sense and avoid systems, establishing robust communication links, and overcoming regulatory barriers. Improving energy efficiency and extending flight endurance are crucial for enhancing UAV performance and mission capabilities. Future efforts involve developing lightweight materials, efficient propulsion systems, and advanced energy storage technologies. Sense and avoid technologies are also advancing to enhance UAV safety and collision avoidance capabilities. This includes integrating sensors such as radar, LiDAR, and computer vision systems, as well as developing standards for interoperability and certification. Urban air mobility, or UAM, is gaining traction as a concept envisioning on-demand transportation services provided by UAVs in urban environments. Challenges in this area include integrating UAM into existing airspace, ensuring safety and air traffic management, addressing noise and environmental concerns, and gaining public acceptance. Regulatory frameworks and standards are essential for the safe integration of UAVs into airspace and society. Future trends involve developing international standards for UAV design, operation, and certification, as well as adapting regulations to accommodate emerging technologies and applications. Addressing cybersecurity threats and protecting data privacy are growing concerns in the UAV ecosystem. Future efforts involve implementing robust cybersecurity measures, encryption protocols, and authentication mechanisms to safeguard UAVs and their data. Minimizing the environmental impact of UAVs, including noise pollution and carbon emissions, is increasingly important. Future trends involve developing electric propulsion systems, optimizing flight paths for efficiency, and incorporating eco-friendly materials and technologies into UAV design. Finally, ensuring interoperability and integration of UAVs with other aircraft and systems in integrated airspace operations is crucial. Future developments involve developing interoperable communication protocols, data exchange formats, and collaborative decision-making processes. By addressing these trends and challenges, stakeholders can foster innovation, ensure safety, and realize the full potential of UAV technology for societal benefit. 14. Conclusion. In conclusion, unmanned aerial vehicles, or UAVs, represent a transformative technology with a wide range of applications and potential benefits across various industries. As UAV technology continues to evolve, it is poised to revolutionize aerospace engineering, enabling new capabilities, improving efficiencies, and addressing societal challenges. Key trends in UAV technology include increasing autonomy, the emergence of UAV swarms, advancements in sense and avoid systems, and the rise of urban air mobility. These trends are driving innovation and expanding the possibilities for UAV applications, from surveillance and reconnaissance to agriculture, environmental monitoring, and beyond. However, along with these opportunities come significant challenges, including regulatory barriers, cybersecurity threats, environmental concerns, and public acceptance. Addressing these challenges requires collaboration among industry stakeholders, policymakers, researchers, and regulatory agencies to ensure safe, responsible, and ethical integration of UAVs into airspace and society. Overall, the future of UAV technology holds great promise for enhancing safety, efficiency, and sustainability in various domains. By embracing these trends, overcoming challenges, and leveraging the full potential of UAVs, we can unlock new opportunities for innovation and progress in aerospace engineering and beyond. You have been listening to Aerospace Engineering, the Basics of Aerodynamics, Unmanned Aerial Vehicles. Written by Phil Gilberts. Narrated by Kevin Brooker.